Right, so in the last lecture we talked about alternating series, and that's just one type of series that might not have all positive terms, but there are plenty of others as well. So in 11.6 we're going to talk about a tool that can be used to determine the convergence or divergence of series which are not necessarily positive, which might also not be alternating. So this is called absolute convergence, and the ratio and root tests. Right, so we're going to begin with a definition. So, board seems a little bit close. Maybe I should move it back a bit. And let's adjust this. All right, that's a little bit better, I think. Okay, so let sum from n equal 1 to infinity of an be an infinite series any infinite series whatsoever. We say that the sum from n equals 1 to infinity of the absolute value of an, or sorry, the sum from n equals 1 to infinity of an is absolutely convergent so this is the term, it's absolutely convergent provided that the series sum from n equals 1 to infinity of the absolute value of an is convergent. Okay. Now, I just want to point out something here, because this is important. If you were to take the absolute value of 1 plus -7, well, that would be the absolute value of 6, or actually, absolute value of -6, which is just 6, right? Now, this is definitely not the same thing as the absolute value of 1 plus the absolute value of -7, which would be 1 plus 7, and that's 8. So, seeing as how 6 is not the same as 8, I'm pretty sure that that means that if you have real numbers a and b, then the absolute value of a plus b is not going to be the same as the absolute value of a plus the absolute value of b. Okay? There is a fact called the triangle inequality, which says that this thing on the right will always be at least as large as the thing on the left. But they certainly don't have to be equal. Alright, so for the same reason, that means that if we take the series from n equals 1 to infinity of the absolute value of an, that's definitely not the same thing as the absolute value of the series from n equals 1 to infinity of an. Okay? It's possible that this thing doesn't even converge, in which case taking its absolute value doesn't make sense in the first place. But besides that, even if both of these things do converge, they might not be equal. Okay? So this right here, this is not the absolute value of the series, it's what I would call the series of the absolute values. Okay? Now, thankfully, there are a lot of terms in math that are poorly chosen in the sense that the term makes it sound like something is going to be true for that object, but then it's not actually true. But then you can't change the terminology because it's already ingrained in the literature, so you just have to go with it from then on. This is not one of those examples, okay? So if a series is absolutely convergent, you're probably hoping that it's also going to be convergent, right? The following theorem says that that's true. Okay, so if the sum from n equals 1 to infinity of an is absolutely convergent, then it is convergent. Okay? Now, having said that, the converse of this is false. There are some series which are convergent but fail to be absolutely convergent. Okay? For example, so yeah, let's just look at an example here of how this converse can fail. We want to determine whether the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n is convergent or divergent, let's say. Or let's actually say absolutely convergent. This is more of an illustrating example than an example problem, but so what's going on here is if we were to take the series of absolute values, well, then we'd be talking about the series from n equals 1 to infinity of the absolute value of negative 1 to the n plus 1 divided by n. Now, the absolute value of n is, of course, n, because n is non-negative. So this is the same as the sum from n equals 1 to infinity of the absolute value of negative 1 to the n plus 1 divided by n. Okay? But now the absolute value of negative 1 to the n plus 1, well, let's see here. Negative 1 to the n plus 1 might be 1, or it might be negative 1, depending on whether n is even or odd. Either way, though, the absolute value is still 1, right? Okay. So this is the sum from n equals 1 to infinity of 1 over n. And that's the harmonic series, right? So this series is divergent because, you know, as we said before, the harmonic series is divergent due to the integral test and the p-series test, however you want to say it. So this is divergent. So the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n is not absolutely convergent. Okay. However, this is an alternating series. The sequence of absolute values is decreasing, and the limit of the sequence of the absolute values is 0. So by the alternating series test, it is convergent. So the sum from n equals 1 to infinity of negative 1 to the n plus 1 divided by n is convergent by the alternating series test. So we have this slightly awkward situation where the alternating harmonic series is convergent, but it's not absolutely convergent. And that can happen, okay? What this theorem is saying, though, is that if it is absolutely convergent, then it's convergent. This example is just illustrating that the converse, which is if it's convergent, then it's absolutely convergent, that's actually false, okay? So absolutely convergent means convergent, but convergent doesn't always mean absolutely convergent. I feel like I'm talking in circles at this point, but yeah, that's what I'm trying to say. Now, in this case where a series is convergent but it's not absolutely so, we would say it's conditionally convergent. Okay? So the sum from n equals 1 to infinity of an is conditionally convergent if it is convergent but not absolutely convergent. Alright? So the alternating harmonic series, this example shows that the alternating harmonic series is conditionally convergent. Okay? So I think some of you will think that I'm beating a dead horse when you watch this lecture, but I just want to be really clear about this. So what I'm saying is a series, right? A series could be either convergent or it could be divergent, right? Now, if it is convergent, it's possible that it's absolutely so. So it could be absolutely convergent. It's also possible that it's not, in which case we would say it's conditionally convergent. Okay? And if it's divergent, then it's just divergent. We don't care about it then. Okay? So what this theorem here is saying is that if you can show that something is absolutely convergent, well, that means it's convergent. Okay, so this arrow goes like this. Also, if it's conditionally convergent, then I guess that also makes it convergent, although that's harder to show. Something that came up one time with one student that I was talking to, he was a bit confused because he thought that there was some kind of qualification like these for divergent. That's not true. There isn't such a thing as absolutely divergent or conditionally divergent. That's not a thing. Okay, those aren't terms that we actually use. Okay. So, by this theorem, if you can show that a series is absolutely convergent, then you've got that it's convergent, right? That's actually easier to show often than just showing that it's convergent right from the off. Okay, so why don't we do some examples in which we illustrate that. Let's see here. So let's say Okay, I guess I'm going to have to erase this. So let's say we have an example here. We're going to determine whether the sum from n equals 1 to infinity of the sine of n pi over 3 divided by n squared is absolutely convergent. Or it might be conditionally convergent. Or it might be divergent. Okay? So, if we want to determine whether this is absolutely convergent or not, then we just have to go back to the definition of absolutely convergent. We just need to take the series of absolute values here. By the way, also, I just want to point out, this is not an alternating series. It does have some terms that are positive and some terms that are negative, but they don't flip back and forth every single term. It's a lot weirder than an alternating series, because like, if n is 1 or 2, then this is positive. If n is 4 or 5, it's negative. If n is 7 or 8, it's positive. If n is 10 or 11, it's negative, and so on like that. Okay, so it's weirder than an alternating series, so you're not going to be able to use the alternating series test for it. So, the way that we should handle this is instead we should look at the series of absolute values, the sum from n equals 1 to infinity of the absolute value of the sine of n pi over 3 divided by n squared. So now n squared is, of course, non-negative, so that means that it is its own absolute value. So if we want, we can just write this as the sum from n equals 1 to infinity of the absolute value of the sine of n pi over 3 divided by n squared. Okay? Now, at first that doesn't look easier, right? But I claim it is. I claim it is because the absolute value of the sine is always less than or equal to 1, right? And if the absolute value of the sine is always less than or equal to 1, that means that the absolute value of the sine of n pi over 3 divided by n squared is always less than or equal to 1 divided by n squared. So then this means that, well, if we were to look at the sum from n equals 1 to infinity of 1 over n squared, this is a convergent p-series. So this is a convergent p-series. Then by the comparison test, that indicates that this series is also convergent. Okay, so by comparison, the sum from n equals 1 to infinity of the absolute value of the sine of n pi over 3 divided by n squared is convergent as well. And then by definition, since the series of absolute values is convergent, that means that the original series is absolutely convergent. Okay? So, by definition, the sum from n equals 1 to infinity of the sine of n pi over 3 divided by n squared, this is absolutely convergent. And that's our answer. And this is important because if it's absolutely convergent, then that means it's also convergent, right? So this illustrates a strategy for, a new strategy for determining whether a series is convergent or not. If you can show it's absolutely convergent, you're done. Thinking back to this series, just trying to determine whether that thing is convergent or divergent without doing any of this, that would be really hard, right? Most of the tests we have are for non-negative series, which this has negative terms, so all right, those tests won't work. And it's also not an alternating series, so that's not going to work either. So there's not really a lot that you can do with that, right? You might be able to do some things like break up the sum into two parts like I did in the previous lecture, but don't. Instead, it's much easier to just show that it's absolutely convergent, and then that shows that it's convergent, okay? All right, let's look at another example. So this one is similar. It's going to be the sine of n pi over 6 divided by 1 plus n root n. So this is now n pi over 6 divided by 1 plus n root n. And once again, we're being asked to show whether it's absolutely convergent, or conditionally convergent, or divergent. And once again, this is weirder than an alternating series. Yes, some terms are positive and some terms are negative, but they're not going to alternate. So we do the same thing. We look at the sum of n equals 1 to infinity of the absolute value of the sine of n pi over 6 divided by 1 plus n root n. Now, as before, the denominator is always positive, so you don't have to worry about that. So we just have the absolute value of the sine of n pi over 6 divided by 1 plus n root n. And now, if we can determine whether this is convergent or divergent, well, that will determine whether it's absolutely convergent or not. So, again, the sine has value, the absolute value of the sine has values less than or equal to 1, so we can take the absolute value of sine of n pi over 6 over 1 plus n root n. That is definitely less than or equal to 1 over 1 plus n root n. In turn, this has a larger denominator than 1 over n root n. And n root n, that's the same as n to the 1 times n to the 1/2, which would make it n to the 3/2. So this is the same as 1 over n to the 3/2 power. And once again, this is a convergent p-series. Okay? So the sum from n equals 1 to infinity of 1 over n to the 3/2 is a convergent p-series. And then, again, by comparison, that means that, so by comparison, that means that the sum from n equals 1 to infinity of the absolute value of the sine of n pi over 6 over 1 plus n root n is convergent. So that means the original series from n equals 1 to infinity of the sine of n pi over 6 divided by 1 plus n root n is absolutely convergent. And that's at least one way of figuring that out, right? Let's do one more. So this one is going to be the sum from n equals 1 to infinity of negative 1 to the n minus 1 divided by the square root of n. And once again, we're trying to determine whether it's convergent or absolutely convergent or conditionally convergent or divergent. So if you want to determine whether it's absolutely convergent or not, we're going to have to take the series of absolute values. So the sum from n equals 1 to infinity of the absolute value of negative 1 to the n minus 1 divided by the square root of n. Well, once again, the bottom is positive, so no problem there. So this is just the sum from n equals 1 to infinity of the absolute value of negative 1 to the n minus 1 divided by the square root of n. And then the absolute value of negative 1 to the whatever power is always 1. So then this is the sum from n equals 1 to infinity of just 1 over the square root of n. Which, by the way, is the sum from n equals 1 to infinity of 1 over n to the 1/2, right? Now that is a divergent p-series. Okay? So this is a divergent p-series. What that means is that this thing is not absolutely convergent. Okay? Now, we're not done yet, because now that you've ruled out that it's absolutely convergent, it can't be absolutely convergent, there's still more possibilities there. It's not necessarily convergent. Like, it might be divergent altogether, but at the same time it might be conditionally convergent. So we've got to figure that out now. This one is actually an alternating series, right? So what we can do here is, first of all, if we were to set up Bn, the sequence of absolute values of the terms, like the alternating series test refers to, that'd just be 1 over root n, right? So, if you were to take 1 over root n plus 1, well, that would be what you call Bn plus 1, right? This has a larger denominator, which means that it's smaller. This shows that the sequence of absolute values is eventually decreasing. In fact, it's strictly decreasing. So we have that. Then, if we were to take the limit as n approaches infinity of Bn, that would be the limit as n approaches infinity of 1 over the square root of n, which is just 0, right? This means that by the alternating series test, the the sum from n equals 1 to infinity of -1 to the n minus 1 over the square root of n is convergent. If it's convergent but not absolutely so, then that means it's conditionally convergent. Okay. And this is fairly typical. Like the example that I did to show that the alternating harmonic series is conditionally convergent, and this example, they illustrate a pretty common strategy, probably something that it'll do most of the time. When you're given an alternating series, you're asked whether it's absolutely convergent, conditionally convergent, or divergent. If you find it's absolutely convergent, you're done. You might not. You might get that it's not absolutely convergent, in which case you have to determine whether it's conditionally convergent or not. The easiest way to determine whether an alternating series is conditionally convergent is to do the alternating series test. Of course, that might not apply, in which case it might be divergent, and then you might have to use the test for divergence to show that. Okay. Right, so that's the definition of absolute convergence. And so far all we've done is we've just used that definition and the theorem that says that absolute convergence implies convergence. Now we're going to introduce another more powerful theorem. This one is called the ratio test. So this is the ratio test. Let the sum from n equals 1 to infinity of an be an infinite series. Okay, here's how it goes. What we're going to do is we're going to take the absolute value of an plus 1 divided by an. And that's the ratio that it's referring to. We're going to take the absolute value of that and then take the limit of that as n approaches infinity. Actually, you know what? I'm going to state this a little bit differently than how I do it in my notes. It's correct in my notes, but I just want to state it a little bit differently. Let's define this as L. Okay? Here's how it goes. If L is less than 1, the series converges absolutely. If L is greater than 1, the series diverges. Okay? And that's it. And by the way, L being greater than 1, that includes the possibility that it might be positive infinity. So if it's positive infinity, it diverges as well. Okay? Now, as you can see, this has nothing to say if L is equal to 1. It's not perfect. Okay? If L is equal to 1, then you could have anything happening. It's possible that it converges absolutely, it's possible that it converges conditionally, and it's also possible that it diverges. The ratio test will not be able to tell you about the situation where L equals 1. Okay? But if you have it being less than 1 or greater than 1, then you know quite a lot. And one more thing I want to point out. If a series converges conditionally, then neither of these are true, right? If the series converges conditionally, then it doesn't converge absolutely, but it also doesn't diverge. Which means that if a series converges conditionally, then L will have to be 1. However, the converse of that is false. It's possible for L to be 1 without the series converging conditionally. Okay? And we'll see all of that. Anyway, let's look at an example. So, this example says we want to determine whether the series sum from n equals 1 to infinity of n factorial divided by 100 raised to the nth power is conditionally convergent, or I guess I should say absolutely convergent. Or conditionally convergent. Or divergent. Okay. And by the way, hopefully you've seen this before, n factorial. That just means 1 times 2 times 3 times 4, dot, 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 all the way up to n. So for example, 5 factorial, this is 1 times 2 times 3 times 4 times 5. And in this case it happens to be, let's see here, 6 times 20, so that makes 120. Okay. So let's look at how this works. The ratio test is most useful when you have some kind of exponential or some kind of factorial, because those two functions have particularly nice properties in terms of cancellation, and they make the ratio that you're dealing with pretty easy. So let's see how this works. What we're going to do is we're going to try to use the ratio test. So we have to take the limit as n approaches infinity of the absolute value of an plus 1, so the n plus first term, divided by an, which is the nth term. So what that literally means is we're going to take the n plus first term, so this is the limit as n approaches infinity. N plus first term is going to be on top, so that's going to be n plus 1 factorial divided by 100 raised to the n plus 1. All of this is divided by n factorial divided by 100 raised to the n. Okay, so you're just taking the term when you plug in n plus 1 as the index, and the term when you plug in n as the index, and dividing an plus 1 by an. And by the way, it does matter that it's an plus 1 over an. If it's the other way around, then the ratio test, it can be rephrased, but it's going to be different. It's not going to apply in the same way. Anyway, This is the limit as n approaches infinity of the absolute value of, all right, so we want to take this fraction and divide it by this fraction. The way to do that is to take this top fraction and leave it alone. So we're just going to copy this. So n plus 1 factorial over 100 raised to the n plus 1. Rather than dividing from here, now we're going to multiply. Multiply this by, and then flip this fraction upside down. So that's going to be 100 raised to the n divided by n factorial. Okay? That's how you divide fractions, right? When I was in high school, this procedure was called copy, change, flip, because you copy the numerator, change the division to a multiplication, and flip the denominator. I don't know if you've ever heard that phrase before, but that's what was used. That's what was popular when I was in high school back during the Punic Wars. Right, so you have this. Now, of course, the absolute value signs don't really matter much in this case. In this case, because everything's positive here, right? So, whatever. Forget about the absolute value, that's not important. We have 100 copies of n multiplied together. Or, sorry, I said that wrong. We have n copies of 100 multiplied together on top. And we have n plus 1 copies of 100 multiplied together on the bottom. That means that n many copies of 100 will cancel, so we'll just be left with 100 on the bottom. Another way of seeing this is to subtract the exponents. Okay? So we're going to have the limit as n approaches infinity of something over 100 raised to the first power. The other thing is n plus 1 factorial divided by n factorial. So let's think about this for a second. N plus 1 factorial, that'd be 1 times 2 times 3 times 4, all the way up to n minus 1 times n plus 1, right? So let's go ahead and just write that out for a second. So we have n plus 1 factorial. That's 1, 2, 3, all the way up to n minus 1 times n plus 1. Meanwhile, we have n factorial. This is 1 times 2 times 3, all the way up to n minus 1 times n, and that's it. And you're dividing these. So now, 1 cancels with 1, 2 cancels with 2, 3 cancels with 3, n minus 1 cancels with n minus 1, n cancels with n, and what you're left with is just n plus 1. Okay? And that's why I said before that the factorial has nice properties in terms of cancellation. So n plus 1 factorial divided by n factorial is just n plus 1. So this is now just n plus 1 divided by 100. You take the limit as n approaches infinity, and of course that's infinity. Okay? So what infinity is of course not less than 1. So by the ratio test, the series diverges. Okay? Let's look at another one. This one we have negative 2 to the n divided by n squared. So on top we have negative 2 raised to the nth power divided by n squared. And once again, we're trying to determine whether this is absolutely convergent, conditionally convergent, or divergent. So in this case too, we can use the ratio test. Again, we're going to take the limit as n approaches infinity of the absolute value of an plus 1 divided by an, which in our case is the limit as n approaches infinity of the absolute value of, let's see here, the top is going to be negative 2 to the n plus 1 divided by n plus 1 squared. So that's the numerator. The denominator is going to be an, the nth term, or in other words, negative 2 to the n divided by n squared. Again, you do the whole copy, change, flip thing. You say this is the limit as n approaches infinity of the absolute value of negative 2 to the n plus 1 divided by n plus 1 squared. Change the division to a multiplication and flip the bottom, so you get n squared divided by negative 2 to the n. Now, negative 2 to the n plus 1 divided by negative 2 to the n is just negative 2. So this is going to be the limit as n approaches infinity of the absolute value of negative 2 n squared divided by n plus 1 squared. Everything here is positive except for this negative sign. So when you take the absolute value, the negative sign just disappears. So this just becomes the limit as n approaches infinity of 2n squared divided by n plus 1 squared. And now there are a few different ways to take that limit. The easiest way would be to divide top and bottom by n squared. If you do that, then you'll see that this is going to approach 2, which is greater than 1, right? So again, by the ratio test, the series diverges. And that is how we would do that one. Okay. All right, so the last thing we should talk about for today is called the root test. The root test is similar, but it's a different object that you're working with. So theorem, this is called the root test. Once again, let the sum from n equals 1 to infinity of an be an infinite series. And let's say define L. In this case, I'm going to let L be different. In this case, L, I want to be the limit as n approaches infinity of the nth root of the absolute value of an. And then the conclusion is exactly the same. It just says if this limit is less than 1, the series converges absolutely. And if this limit is greater than 1, or infinity, it diverges. Okay? So this one has this one, as you can see, is similar in structure, but its utility is a bit less, just because you really only use it for weird series that have some kind of n as an exponent thing going on. Which, I guess that happens for geometric series. But, if it's a geometric series, you wouldn't even care about this, because you already have a theorem that characterizes those. But also it could happen for a few other series. So, yeah, why don't we just do an example? So this is going to be the sum from n equals 1 to infinity of, let's see here, we've got 1 minus n divided by 2 plus 3n, and all of this is raised to the nth power. And we're once again trying to determine whether that's absolutely convergent, conditionally convergent, or divergent. Okay? So this nth power here, that's what you're really looking for when you're doing the root test. It can come in other forms as well. It could be like the 2nth power, or the n plus 6th power, or the n squared power. All of those too, the root test would be at least a good thing to think about. But yeah, you're always going to have some power that's dependent on n in some way, and that's kind of a dead giveaway that the root test is what you're going to be using. So let's look at how this works. We want to take the limit as n approaches infinity of the nth root of the absolute value of an. Okay, let's see here. In our case, an, okay, so we need the nth root of, let's see here, absolute value of an is going to be the absolute value of 1 minus n raised to the nth power, 1 minus n over 2 plus 3n raised to the nth power. Now, everything here is non-negative, so you don't really need that absolute value, right? So this is the same thing as just the limit as n approaches infinity of the nth root of 1 minus n divided by 2 plus 3n raised to the nth power. You take something to the nth power, and then take the nth root of that. Well, of course, those two actions undo each other. So then this is just the same thing as the limit as n approaches infinity of 1 minus n divided by 2 plus 3n. Wait a second. No, I misspoke. It's small, but I did make a mistake here. 1 minus n is most certainly not non-negative. In fact, 1 minus n is going to be negative as long as n is greater than 1. So yes, we actually do need to care about the absolute values here. In that case, we can just take it inside the exponent. So we can just say that this is the absolute value of 1 minus n divided by 2 plus 3n raised to the nth power. Okay. And then, like I said, nth power of something raised to the nth is just that thing. So then, nth root of something raised to the n is just that thing. So then this just becomes the absolute value of 1 minus n divided by 2 plus 3n. It turns out that the absolute value function is continuous. So that means that this is the same thing as the absolute value of the limit as n approaches infinity of 1 minus n divided by 2 plus 3n. As n approaches infinity, this thing approaches negative 1/3. So this is the absolute value of negative 1/3, which is positive 1/3. I'm pretty sure that's less than 1, right? Okay. So what that tells us is that by the root test, the series converges absolutely. Okay. And I'm looking through my notes here. For some reason, I do have it. It's sort of in the section on power series. I really like that though, so I'm going to do one more example. I'm going to do one more example with the ratio test. I want to look at the sum from n equals 0 to infinity of 1 divided by n factorial. Now, let's think for a second about how you would do that without the ratio test. Well, let's see here. Integral test won't really help you much because in order to take the integral of the factorial function, that won't make much sense unless you know about, well, unless you know some other math. So integral test won't really help here. It's definitely not geometric. It's definitely not telescoping. Comparison test would be great, but first of all, what are you going to compare it to? I mean, n factorial, that's just whatever n factorial is. And then it's not an alternating series. In fact, it's a series of positive terms. So how would you do this? Well, the easiest way to do it, I say, is by the ratio test. Here's how it works. We're going to take the limit as n approaches infinity of the absolute value of an plus 1 divided by an. That is the limit as n approaches infinity of the absolute value of, let's see here, 1 over n plus 1 factorial. And then this is divided by 1 over n factorial. Again, you do the whole copy, change, flip thing. This becomes the limit as n approaches infinity of the absolute value of 1 over n plus 1 factorial times n factorial over 1. Everything is positive, so we can forget about the absolute values. So this is now the limit as n approaches infinity of n factorial divided by n plus 1 factorial. Again, n plus 1 factorial divided by n factorial is just n plus 1. And this is 1 over that. So this is limit as n approaches infinity of 1 over n plus 1. So n approaches infinity, this approaches 0, which is less than 1. Okay? And so, by the ratio test, the series is absolutely convergent. Okay. And actually, I just want to point out here, in this case we have a series with positive terms. So that means that all the terms are their own absolute values, which means that absolute convergence is synonymous with convergence in this case. Okay? Because, of course, if this thing is convergent, then it's also absolutely convergent because it is the series of absolute values. Okay? So, just wanted to end with this example because this series right here, well, we just found that it's convergent, right? It's absolute convergent, therefore convergent. Turns out that the sum from n equals 0 to infinity of 1 over n factorial is at least one way of defining the number e. Not that that's important, just a little weird fact. Anyway, that's all for today. Homework is up. Go ahead and get some practice with that.